Okay, so our next speaker is Angela Martini.
Thank you. My name is Angela Martini, and I'm a UMD electrical engineering student. I work with the Aspire Lab. I will just share my screen now. So, oh, I have to go on to slideshow. Sorry. There we go. Okay, so my project is on respiration monitoring utilizing wearable stitch strain sensors through the Aspire Lab at UMD. But the introduction and inspiration of this research started with the idea of wearable vital monitoring of female astronauts, which tend to be disproportionately injured during EVA and IVA activity on the ISS and beyond. Not only for space travel, this tech could also be used anywhere to prevent injury caused by equipment, worn being the key, and to simulate the chest expansion. Testing with the min strain measures the resistance of the conductive thread in the samples, just as the garment would simulate during breathing. This relates to the ability to count respiration rates, and also measuring the resistance versus displacement, as well as the stress versus strain relationships, simultaneously allowing understanding of material properties related to the displacement of the stitch sensor when being worn. Objectives with this project was to create wearable vital monitoring using stitch sensors and e-textiles, determining the resistance of the conductive thread when stretched or under strain in order to measure respiration via chest expansion with the garment. So typically chest expansion during breathing is about 2 to 5 inches. So developing a safe, user-friendly interface makes the garment much more practical. Measuring chest expansion and contraction during breathing relates to the respiration rate observed. And to improve the tensile testing apparatus, which we were first presented, to measure resistance versus displacement, as well as the force versus displacement and strain measured. So existing methods to measure breathing rates now are spirometry, which is breathing into a tube apparatus measuring ventilation and movement of lungs using a spirometer, which is accurate, but it's very invasive and not very practical for everyday use. Doppler radar systems, these sensors are pretty accurate, and although when you move around a lot, it might tend to not be. They monitor all types of vital signs of subject in an area, but if you move out of the area, you're kind of unsensed, to say the least. And then counting breaths per minute, it's free, but it could be inaccurate. So that brings us to our research gap, which is simple, cost-effective stitch sensors, which are easily worn under spacesuits, and a reliable method to measure breathing rates. The materials and equipment used in this project consist of the fabric, which is 87% polyester and 13% elastane and a 4-way stretch. Each sample size is 12 centimeters by 4 centimeters. The min strain apparatus, the furthest to the right, is what measures our displacement, force, resistance, time, engineered by a former master student, Stin Van Dyke. The conductive thread is a 1,000 ohm silver ply material sewn 10 centimeters across each sample. And then this was sewn onto it with, this is actually the stitch sensor itself, is just the thread. I had to make that point, sorry. And then it's sewn into it with that brother cover stitch, which weaves it on top. And then we'll get to the next slide. This is our prototype of the respiration monitoring e-textile. So using these soft textile-based sensors offers us important wearability advantages, such as flexibility, conformable to the body's curves. It's comfortable and user-friendly. It integrates into clothing easily for proximity to body surface. It's also customizable and maintainable. You can we're just focused on respiration at the moment, but we can monitor all kinds of vital signs such as heart rates and other vital signs. So this is a circuit here that's going to be connected into the stitch sensor circuit. I like to call it TIM in 818 from, and then this is going to be put into this part right here. I'm not sure if you can actually see my mouse, but it'll be on the garment in the future. But we're still in prototyping phase. Sorry about that. And then, so we've done so much work to get an analog to digital converter for more accurate testing. We started here, I don't know, maybe about 6-7 months ago with an Arduino Uno via breadboard. This is our ADC that we're talking about here. And then we moved on to the PCB board, also connected externally to the Arduino Uno. Not very user-friendly yet. So finally, we get the ADC to make its final resting spot into the MINS train. This is all torn apart. We've done a lot to this, but it makes the interface as convenient as possible, and it's super easy to use, and I actually really enjoy doing the testing itself now, so that's a good thing. So this shows a little bit more intricate modifications to the MINS train. We use a voltage divider circuit. And so this is kind of how it works. It goes through these two resistors, and then the bigger resistor is actually what determines the unknown resistance from the stitch sensor going to the ADC, and then ultimately the microprocessing unit, which is the Arduino Mega inside this apparatus. Methodology. So the material properties testing consists of each one of these samples is what it actually looks like going into the apparatus. I measure the thickness, average thickness via thickness gauge to further, that's going to come later with the stress versus strain. Okay, I have 6 samples composed of the 87% polyester, 13% elastane. Do about 6 samples per cycle, measuring sensor response and in resistance in ohms and the displacement and the force. And that brings us to wearable testing in our future work, which will potentially be on human subjects during sitting, standing, and walking. So our testing process, each sample is inserted into the clamps on the MINS train apparatus, then stretched to 1,068 millimeters to measure the displacement versus resistance relationship per sample. Each is tested 6 times per sample. The data is then processed by the Arduino Mega inside the MINS train and then transferred to a PyCharm program, which must then be imported into Excel for analyzation and results. Each test takes about 197 seconds to completion. So, excuse me. The software applications utilized are the Arduino IDE, which is communicating to the MINS train's internal Arduino Mega. And then that goes to the PyCharm, which collects data to the MINS train tools folder, and then goes to Google Sheets to import the data collected to show results. And here's our results. These are the preliminary results. We finally got the tinsel tester to work in March. So we just started in March with actual testing. But it does show a linear average. It's pretty consistent between all of them. There are slight variances in composition and getting stretched. Slight differences in the actual stitch itself could show a little variance, and so we got an average, and it shows resistance goes down as it's being stretched, which simulates the breathing pattern. So if it were to go up and down like that, that's what it would show, but this tinsel tester only just stretches it, so that's what you're seeing here with going down like that in the graph. And then this brings us to the elastic modulus. And as I mentioned earlier, your chest expansion with breathing is only about 2 to 5 inches. So we had to cut the data down to show just about 20% strain, subtracting the pre-strain value to show you what you see here today. And here's actually a sample, which you can't really see too good because it's blue like the background. But it's connected to these alligator clips, and that's what connects it to all of our technology that's going on that you can't see in the picture. And so this explains the stress versus strain elastic modulus. this is up to 20% strain, subtracting the pre-strain value as previously mentioned, showing the linear average. So I put this slide in to show the entire range of data on top, which would not be likely for a garment simulation. And on the right shows the 20% strain, which is much more feasible to be observed in a garment as someone's actually breathing normally without being overstrained. And then conclusions, we did develop the garment to track breathing in real time to potentially allow physiological monitoring of astronauts. We retrofitted the menstruating tensile tester to measure resistance of conductive thread at the same time as force and displacement. We measured conductive stitch sensor material properties and the resistance versus displacement relationship necessary to detect breathing rate. And also the stress versus strain relationship showing strength of material. Future work is to test and evaluate the stitch sensor embedded in a garment and ultimately start human testing of respiration monitoring in our garments, and to measure the resistance and stress versus strain relationship after the samples have been laundered, and respiration monitoring during activities in space such as walking, sleep, sitting, as much as you can in space anyway. References and acknowledgments. And if there's any questions, I would be happy to answer.
Thank you very much. So as I did with the last speaker, this project has pretty obvious NASA connections, but can you say a little bit more about who might be interested in these results who are not astronauts? I mean, doctors, clinicians?
That's a great question, actually. So we also have firefighters in mind. That's also goes hand in hand. I didn't really mention it because we're talking space applications. But anywhere where you really have strenuous activity or some sort of breathing problem, any kind of, yeah, doctors would be totally, I think, interested in it. And you can pretty much use it anywhere there's a concern for breathing rates, and then we're ultimately going to get to further vital sign monitoring. I hope that answered the question. I'm sorry if it didn't.
No, it was great. Thank you.
Okay.
One more question, and that is, you stitch these things and the stitches go back and forth. And so when you pull on them, the back and forth is more spread out.
Mm-hmm.
Why does that produce a change in resistance? Or
Well,
is the material itself, when you pull on this particular material, it actually changes its resistance and it wouldn't have to even go back and forth?
it strains resistance and then it goes down as it's being pulled, and that simulates the breathing patterns. And
That's okay. That's just something I've never
I'm
quite
like,
understood. I've never quite understood about wearable technology.
What materials are these stitches made of?
The fabric itself or the thread?
The thread. What you're using to detect the changes in tension?
It's a silver ply thread. It's covered in silver is the material that actually has the conductive properties in the thread that we're measuring up with the alligator clips. If that answers.
It does.
Okay. Yes. Sorry.
Yep. Any final question? One more question?
So, Angela, can you describe what the cover stitch bottom thread looks like? Because it might, or maybe go back to the slide and show people what that cover stitch bottom thread looks like, the shape of that thread.
So the bottom looks like a normal stitching, but the actual conductive property, it just weaves it on top. Oh, I wish I had a picture of that. That's a good point.
So when you strain that, what happens to the thread?
The thread gets stretches and it gets longer, and that's when the resistance goes down.
And the width gets narrower, right?
Yes.
As well.
That's what I'm trying to say. Thank you.
Yeah, no worries. So we have.
Great. We better go on. Thank you so much.
All right. Thank you.